What the heck?
Hectogon.
What are you looking at? Hi, Gus. All right. So we have ourselves a fantastic video for you today. We're going to be proving some of my favorite results from real analysis today, and it's a little unfortunate that they occurred this early on, but there's plenty of good stuff to come after this. But we've got some of my favorite results today. So we're going to cover the topic of cardinality, and we're going to utilize that topic of cardinality to discover something very, very neat about the real numbers. And we're going in two different ways. One of them will involve the nested interval property, and one of them will not. One of them will use a different method of proof. At least in this context, it's a sort of different method of proof. It seems it's a bit more constructive, I would say. Well, maybe it's not constructive, but that's beside the point. I'm going to show you two different ways to show something pretty amazing about the real numbers using cardinality, and I'm going to talk about power sets, and we're going to cover something called Cantor's theorem. Here comes the dog to come sit under the desk. Hello, puppy. Oh, who's a good boy. Okay, so today we're going to cover the topic of cardinality. So what is cardinality? How do you spell that? So cardinality. So what is cardinality? So cardinality is, in some sense, the size of a set of objects. How big is a set? How many things are in it? And so quite intuitively, cardinality, when asked about a set with a finite number of things in it, the cardinality of that set is simply the number of things inside that set. So if the set A was the collection of 1, 2, and 3, then we would say that card A, or this, right, that's one way of writing it. It almost looks like absolute value. And in this case, it would just be 3, right? Because there are 3 elements in the set, and so the cardinality is 3. When the size of the set is finite, then cardinality means the same as the number of things in the set. So if that's cool with you, then that's cool with me. Where did I put my eraser? Where's my eraser? What have I done with it? What have you done with it, dog? There it is. If two things have the same amount of things in them, then they have the same cardinality. So for example, if the set B was 4, 5, and 6, right, it's not too hard to see that we can clearly see that both of these had a cardinality of 3, and so we can say that they're the same size. They have the same number of things in them. We need some method that we can apply to infinitely large sets that will also tell us if there's the same number of things in them, that will also work when there are finite things. So some method that I can use for this that generalizes to infinite sets as well. And that's going to be using what we discussed in the first video, which was bijections. So we need some rule that's going to map one element of one set onto another for every element in one set, without running out of any of these and without maybe doubling up on any of these. So the whole point is we want to find a bijective function from A to B. And if we can find a bijection from A to B, we also can find an inverse of that, which would take us, or not necessarily an inverse of that function, but another bijection from B to A. Because if everything is uniquely mapped onto one element of these and you use up everything in both, you can easily go backwards and find the original thing that mapped onto that. So if they're the same set, we can find a bijection from one to the other, regardless of which one we start with. And remember, a bijection is a function that is injective and surjective, which means everything in here gets mapped uniquely to one element of here, and everything in here is hit, right? The injection is that each of these maps onto one of these, and the surjection is that each of these are hit, right? And of course we go in the other direction, it doesn't matter. So a bijection is a function that is a surjection and an injection. In other words, it's one-to-one and onto. We also call a bijection a one-to-one correspondence. So a one-to-one correspondence is a function that is one-to-one and onto. Put another way, it is injective and surjective. So it's a unique mapping for every single element, and if we can do that between two sets, then we say that they have the same cardinality. So, for example, let's think about an infinite set that's easy to consider. So let's consider the natural numbers. So the natural numbers are the set 1, 2, 3, 4, forever, right? They're just the set of all the natural numbers, the set of all the positive integers, I should say. And say we want to compare that to the even numbers. Do these two sets have the same cardinality? At first glance, you might think no, because, well, this is only half the natural numbers, right? We don't have 1, we don't have 3, we don't have 5. But putting a little more thought into it, you can see that there's quite an obvious bijection, right? So if we want, so we'll call this the set of even numbers like that with that double barred e. So we want to find a bijection from n to e, right? If we can find a way to assign each element of n to a unique element of e such that each element of e is hit once, then we have a bijection, right? And it's not too hard to see what that is. Just map every number onto its double. Our function f can simply be f of n equals 2n for all n in the natural numbers, right? And all that means is 1 goes to 2, 2 goes to 4, 3 goes to 6, 4 goes to 8, right? We map every number onto its double, and you see that we will never run out of both. Each element of n goes to one element of e, and every element of e is hit, which means this is a bijection, and that works just fine. We could, of course, go in the opposite direction, because every bijection has a well-defined inverse. We can do the inverse as simply being n over 2, in which case 2 would go to 1, 4 would go to 2, 6 would go to 3, 8 would go to 4, and this would be the inverse function from e to n, right, if we did that, right? So the inverse goes in the opposite direction, and so we would just invert the equation, right? The opposite of multiplying by 2 is dividing by 2, so that's the inverse. Either way, it's a bijection, and it works just fine as an example to show that there are the same number of even numbers as there are whole numbers. As there are natural numbers. An interesting thing to try would be to see, check the integers, right? All of the integers. So this should be a little more tricky, because instead of doing a unidirectional infinite list, we have a bidirectional infinite list, right? Because we have -2, -1, 0, 1, 2, ... Right? Now, what we want to do is we want to actually separate this list into two different lists of numbers. So we want to set z is the union of the natural numbers and 0 with the negative numbers, right? Right, so the integers, all of the integers, is the union of these two sets. So what we're going to do is we're going to have all the odd numbers be associated with these numbers, and we're going to have all the even numbers be associated with these numbers. I hope that's clear. We're trying to make a bijection from n to z, right? So we need each of the members of n to be mapped onto only one member of z, and every member of z has to be hit. So we want 1 to go to 1, we want 3 to go to 2, we want 5 to go to 3, and every odd number is going to go to a natural number. And then every even number in the natural numbers is going to go to one of the elements in this set. So 2 is going to go to 0, 4 is going to go to -1, 6 is going to go to -2, and you'll notice that if we do figure out a way to do this with all the odd numbers and all the even numbers mapping onto the natural numbers and the non-positive integers, respectively, then we will have a bijection, right? Every member of the integers will be hit by one element of the natural numbers, and so it will be a bijection from one set to the other. So let's come up with a rule for this part. So let's write it up here. We don't need the word cardinality anymore. So for us to make a bijection from n to z, we need for all the odd natural numbers to be mapped onto all the natural numbers. So we're saying that f of n is going to be a piecewise function, and so it's going to go to n plus 1 over 2 if n is odd. So if n is odd, it's going to go to n plus 1 over 2. Let's make sure that works. So 1 plus 1 divided by 2 is 1. 3 plus 1 divided by 2 is 2. 5 plus 1 divided by 2 is 3. So that rule works for that. Now we just need to come up with a way to explain this rule on the side here. It shouldn't be too hard. So this is just going to be n minus 2 over 2 for n even. Because let's check that. So n minus 2 over 2, that's the rule for that one. So 2 minus 2 divided by 2 is 0. Whoops, I apologize. My mistake. That should be 2 minus n over 2. So 2 minus 2 over 2 is 0. 2 minus 4 over 2 is -1. 2 minus 6 over 2 is -2. And so this all works perfectly. The rule works for this one as well. And so we have a rule that takes each integer n and maps, each natural number n and maps it onto one of the integers. And so we have a bijection from n to z. We've been able to hit every single member of z with one number of n, and every single number of z is hit, right? Each member of n hits one member of z, and every member of z is hit. That's a bijection, so we've satisfied the requirement. We see that n and z are the same size, and so they must have the same cardinality. And so we would say that card n is equal to card z, which is also equal to card of the even numbers, right? That's what we did before. And so, of course, this is also equal to the cardinality of the odd numbers, right? I guess that would be the symbol for the odd numbers if you did an O for odd. Because, of course, the even numbers are just all the odd numbers plus 1, so you would just add 1 to the rule that we did for mapping n onto E. And there's one more set that I want to check that's actually going to be of the same size as n, and it's not obvious at all. And that will be the set Q, the rational numbers. So we proved before that the rational numbers are dense in the real numbers, which is to say that between any two real numbers, a and b, there are infinitely many fractions between any two different real numbers, a and b, no matter how close they are together. So that's to say that over any interval, no matter how small on the real number line, there are infinitely many fractions. And yet I am claiming that I can list them like I do any of these other sets, because associating them with the natural numbers is essentially listing them, right? There's the first one, the second one, the third one, the fourth one. And so essentially what I'm going to show is that I can also list all the fractions in this way. How am I going to do that? Well, let's see. So what I'm going to do to prove that the fractions are countable is I'm going to assume that I have the set of fractions where all of them are in simplest form. So each fraction only appears once and it's in simplest form. So there's no 2/2, there's no 3/3, right? It's just all the numbers appear in simplest form. So we will call a set Qn if it satisfies this property. Will be the set of numbers p divided by q, where p and q are integers, and the absolute value of p plus the absolute value of q is equal to n for some natural number n. Right? That's how we define Qn. So Q0 is quite simply all the fractions for which the absolute values of their numerator and denominator add together to give us 1. And there's only one fraction that does that, and that is the fraction that equals 0. 0 over 1. Right? You might think, well, 0 over -1 works, but 0 over -1 is just equal to 0 over 1, because 0 divided by a non-zero number is 0. So this is the set that contains 0. Q2 is also just as simple, or not just as simple, but quite simple. It's -1 over 1 and 1 over 1. Because if you took the absolute values of the numerators and denominators of both of these fractions and added them together, you would get 2, right? The absolute value of -1 is 1, plus 1 is 2. 1 plus 1 is 2. Q3 is also quite similar in that it's -1 over 2, or I guess I should put them in numerical order. So -2 over 1, -1 over 2, 1 over 2, 2 over 1. So that's all the fractions. If you were to take the absolute values of their numerators and denominators and add them together, you would get 3. Right? There's no other fractions that are in simplest form that satisfy that relationship. Q4 is, of course, -3 over 1. We will not include -2 over 2 because we already have -1 over 1, right? We already know that -2 over 2 is equal to -1, so we won't be including it. So nothing to do with 2's divided by 2's because we have both of those fractions there. So we will just have these ones. -3 over 1, -1 over 3, 1/3, and 3 over 1. Notice we are slowly working our way through every single fraction, and we will just continue this forever. And all we have to do is list them out. There's the first one, there's the second, there's the third, there's the fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, and just keep going, right? Just go forever without repeating fractions. If you have something that's not in simplest form, then we already have it, right? If in the next one when we do 5s, right, well that one's going to be fine. But essentially essentially the idea is in each new set we find the fractions that we haven't labeled yet, that we haven't listed yet, where we take the absolute values of their numerators and denominators, add them together, and we get the integer n. And that's how we get Qn. That way, I know I'm going to hit every single fraction. Each natural number is going to hit a single fraction, and each fraction is going to be hit exactly once. And so that, therefore, is a bijection from n to q, which is to say that card n is equal to card of q, which is quite a surprising thing to show. Right? Because this seems like there would be so many more of them because there's infinitely many packed in any interval, whereas all the natural numbers are always 1 apart. A shorthand for this relationship, by the way, is just this. So anytime two sets have the same cardinality, you just put a little tilde between them, and that tells you that they are the same size. And by the way, we're going to make a definition. So we've just shown that n is the same size as q, which is the same size as z, which is also the same size as all the even numbers, of course, and we have pretty much any set that's the same size as n is going to be the same size as all of these. But this one was obviously the most surprising because it seems like that shouldn't be true. But we just demonstrated that it was because I can list them all out and I can label each one as the first one, the second one, the third one, and the fourth one, which means every natural number is getting associated to one fraction and every fraction is hit precisely once. Okay, so here's for a definition. Given a set A, if A is the same size as n, then we say A is countable or countably infinite. So this is the smallest infinity. Now that's a strange thing to say if you aren't familiar with these proofs at all. This is the smallest infinity because if there were any less, right, if we stopped counting at some point, right, we did 1, 2, 3, and we just stopped at some n, then this is a finite list. It has a size of n. It has a cardinality of n, right? Some subset of the natural numbers, only going up to some number n. Then, you know, if we took the size of this, we just get n, right? There are n elements in here. But if we never stop and we keep going forever and ever, we eventually get to a countable infinity, the size of the set n of natural numbers. So at any point before that, we've got a finite amount, but if we never stop, we get to this lowest infinity. It's the first infinity that we reach, because if we stop at any point, we always get a finite amount. That is to say that so that's the first definition, countable or countably infinite. If the size of A is less, strictly less than the size of n, then A is a finite set. Because if A were an infinite set, it would have to be either the size of n or somehow bigger than n. But what does that mean? What would it mean for a set to be bigger than n? Well, this is where the real numbers come in, because we have something to prove. I'm going to prove to you that the size of n is strictly less than the size of the real numbers. Now, what in God's name could that possibly mean? Because this is an infinitely large set. This has infinitely many elements in it. But somehow, some other set with also infinitely many elements in it has more elements? What does that even mean? Well, we have a wonderful argument called Cantor's diagonal argument. Cantor's diagonal argument. And we are going to assume, for the sake of contradiction, that n is the same size as r. So assume that they are the same size for contradiction. We are assuming that this is true only to show that that leads to something that is logically false, logically inconsistent. And so therefore the assumption must have been false, that these are not actually the same size. But we're assuming that they are. Now, it's quite clear that the subset from 0 to 1, the entire interval from 0 to 1, is a subset of R, right? R is the entire number line. This is just an interval on the number line. So if I can show the size of n is less than even the size of the elements, or the size of all the elements in 0 to 1, then of course n is less than R, because this is a subset of that, right? So if I can show this, then it means that this is actually smaller than that, because this is within that, of course, right? And so what we're actually going to assume is that these are the same size, and then show that that leads to a contradiction. So what that means, if I'm assuming that they are actually the same size, that means that I can take each element of n, map it onto a unique element of the numbers between 0 and 1, and every single one of these will be hit. And I'm going to prove to you that that is not possible. So assume that we can associate a number in n to every number in n to a single number between 0 and 1, any real number now. These are not fractions, these are any real numbers we want. And assume that we can do it and that we can list them all, and we will see that we actually cannot. So let's see. This is all of n, so 1, 2, 3, 4, 5, ... And now these are going to be random numbers between 0 and 1. Okay? So just numbers between 0 and 1. I'm just randomly generating long decimal expansions. If they happen to be a fraction, which mean, or if they happen to be a terminating decimal, just fill the rest with zeros, right? Just infinite zeros at the end. And so what we're going to do is just randomly generate numbers, randomly generated numbers, no sense of, sense of picking anything at all. Nothing whatsoever. Just these randomly generated amounts. I'm not thinking about anything in particular when I'm doing this. What would be the next nice one to do? Nothing in particular. I think that should actually really be a 2, if I really wanted it to be. What could be another number? Let's do 1. I don't know that to enough decimal places. I mean, what? I'm not trying to pick anything in particular. Let's do 1, 0, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, whatever. It just goes forever, right? Randomly generated numbers. I'm picking numbers between 0 and 1, and I'm associating them with 1, all the natural numbers. And the assumption is that this is every number between 0 and 1. All of them. Every single one. That's the assumption. That I have been able to list every number between 0 and 1, associate them with a single natural number, and I never run out of both. They both sort of end at the same time. And I'm going to show you that this cannot possibly be true by using Cantor's diagonalization argument. So let's build a new number between 0 and 1 that is for certain not on this list, which would provide the contradiction that we were looking for. So let's consider the first digit of the first number, the second digit of the second number, the third digit of the third number, the fourth digit of the fourth number, the fifth digit of the fifth number. Of course, had I drawn this perfectly with all of the digits the same size, that would just appear as a diagonal of digits down the center. That's why it's called the diagonalization argument. But I didn't draw it perfectly well, so I apologize for that. But essentially, we are taking the nth digit of the nth number on the list. And what we're going to do is we're going to turn each digit into a 1 if it is not a 1. And if it is a 1, we're going to turn it into a 0. Okay? That's what we're going to do. So if it's not a 1, make it a 1. So 0 point... Oh no, we're not going to do 0, because there's a chance that there's theoretically a chance that we could end up with 0. But yeah, so I need to be sure that I'm going to... Sorry. So we're going to take every number, and if it's not a 1, we're going to make it a 1. And if it is a 1, we're going to make it a 2. Okay? So 3 is not 1, so the first digit of our number is 1. 7 is not 1, so the second digit is 1. 1 is 1, so the third digit is 2. 2 is not 1, so the fourth digit is 1. 0 is not 1, so the fifth digit is 1. And so on. We just carry on like that, going farther and farther down the list, taking the nth digit of the nth number and comparing it to 1. If it is 1, we're making it 2, and if it is not 1, we are making it 1. And this is a new number that is strictly between 0 and 1. Right? Is this number on the list? Well, if it were on the list, that would mean that it's equal to one of the numbers on the list, correct? But it's not equal to the first number, because the first digits are different. It's not equal to the second number, because the second numbers are different. It's not equal to the third number, because the third digits are different. And so on. It's not equal to the nth number on the list, because the nth digit is different from that. And that's to say that it is different in some position to every number on the list, which means it is not equal to any number on the list, which means this number is not on this list. This is, whatever it is, as far as it goes, forever and ever, it's not on this list. Guaranteed. And you may think, well, Mr. Hectogon, we can just take this new number, append it to the beginning, and start again. But of course, that doesn't stop me. I can simply do the same process again, and I will always, always, always be able to come up with a new number that is for certain not on this list of numbers, which means I will never be able to complete this list of every number between 0 and 1, which means I cannot find a bijection. There does not exist a function, a bijection, I should say, from n to r. We cannot find a function that is a bijection from n to r. It's not possible. R is literally bigger. We have just shown that n is the size of n is strictly less than r. We did that by showing that n is strictly less than a subset of r, but because that is a subset of r, the interval from 0 to 1, it must be the case that r is bigger in total. And what does that tell us about the rational and irrational numbers? Well, we know that the real numbers are a union of the rational numbers and the irrational numbers. Right? Maybe that's the symbol for irrational, a double-barred I. But we already showed that cardinality of Q is the same as n. But if the cardinality of Q is the same as n, then that means the cardinality of the irrational numbers cannot be the same as n. It must be bigger. Because if it were the size of n, we could just take one element from here, then one element of there, then one from there, then one from there, then one from there, then one from there, and we could show that the union of two countable sets is the same, is also countable, right? It's the same size as n. So for this total set to be what we'll probably call uncountable, right? Bigger than countable infinity, that means that this set has to be a bigger infinity. It has to be bigger, right? It has to be the case that these are the same. Right? The size of R is the same as the size of the irrational numbers, which is just a mind-boggling thing. We've encountered one irrational number so far, the square root of 2. And in fact, the square root of any other non-square numbers and the nth root of any non-nth power numbers are going to be irrational. But we only know of maybe a handful, right? A countable list, even. We only know of a countable amount of irrational numbers, and yet we've just shown that the irrational numbers has to be an uncountable set, right? What have we just shown? So that's a definition, right? Anything that's the same size as n is countable. So if a set A is strictly bigger than the size of the set n, then A is said to be uncountable, or uncountably infinite, another way of phrasing it. And because Q is countable, right, we showed that Q is the same size as n, we can take every element of n and map it onto Q and it's a bijection. If you're unioning that with another set and you get an uncountable set, well then the set you combined it with must be uncountable. So even though we're only aware, most of us are only aware of a countable number of irrational numbers in the sense that we could start listing them, right? There are uncountably many. So even though the rational numbers are dense in the real numbers, these are like somehow denser. There's just so many more. There's way more irrational numbers than there are rational ones, even though we only know of so many, right? And that's just an amazing fact. So we've shown this, that the size of n is not the same as the size of the real numbers. That's what we have shown. The cardinality of n is strictly less than the cardinality of R, which is just an amazing fact. Pretty brilliant. There's something called the continuum hypothesis that asks if there is a set whose size is strictly between those of the natural numbers and the real numbers. But nobody knows. Nobody knows the answer to that question. In fact, the axioms of set theory are consistent with this being true, that there does exist a set like this, and is consistent with this being not true. And so it's an undecidable question given the axioms of set theory, which is kind of an amazing thing. The continuum hypothesis is unanswerable given what we understand about set theory for now. It's probably always going to be undecidable. I don't understand the proof. I've never even bothered to read it or try remotely because I'm not a set theorist, but that is a true fact, right? We do not know if there is something in between the two sizes. Our math is consistent with there being that set and with there not being that set, so it's kind of funny. So that's what we've shown, right? The natural numbers are not the same size as R. There are simply more real numbers than there are natural numbers, even though there are infinitely many natural numbers. And in particular, there are more irrational numbers because we showed that the rational numbers and the natural numbers are in fact the same size. So I'm going to prove that same thing again, but I'm going to use a different method. I'm going to use the nested interval property to prove it this time. So we're going to prove the same result, pretend that we don't know it, and I'm going to use the nested interval property instead. So we're going to do another proof by contradiction that, again, assumes from the start that n is in fact the same size as R. So we're going to prove that they're the same size. That means that there exists a bijection from n to R. There is a function that is 1-to-1 and onto from n to R, right? That's what we want to show. There is a function from n to R that is 1-to-1 and onto. So a function f from n to R. F is 1-to-1 or injective and onto or surjective, right? That tells us that that is essentially saying that we can list the real numbers. So f of 1 is going to be some real number x1, f of 2 is going to be some real number x2, f of 3 is going to be some real number x3, and so on and so forth. And in this one, we're not going to assume that we're just looking at the subset of the real numbers from 0 to 1. We're going to assume that this is all the real numbers, from negative infinity to positive infinity. Every real number appears on this list, every single one. We're going to show that this is not possible. We're going to show that we can find a number x which is not on this list, right? And so therefore, there's no way we could possibly have listed every real number, because we assumed that we've used up all the natural ones, and yet we're going to find one that's not on this list. And we're going to use the nested interval property. So to use the nested interval property to prove this, we want to develop a set of nested intervals with this property. So the n plus first interval is, and the nth real number on the list is not an element of the nth interval. So the nth interval is precisely an interval that does not contain the nth element of the list. So x1 is not in I1. So it's essentially going to be like this. So we have the real number line. Here's x1. Here is I1. So this is, this is I1, this interval right here. Maybe this is x2. And then I2 is going to be inside of I1 and doesn't contain x2. And we're just going to move into the middle, right? We're just going down forever. So then there's x3 inside there, and then I3 doesn't contain x3, right? It just goes in forever, like that. So each in is a subset, or I'm sorry, an interval that does not contain xn, right? And so remember, we pretended that every single real number, or we assumed that every single real number, x sub n, or whatever they are, is on this list. Every single number on the number line. And we're associating each of them with one of the natural numbers, in particular 1, 2, 3, all the way up to n, and forever past that. And we're going to show that this reveals a contradiction. And so what we want to do now is invoke the nested interval property. So let's consider the nested interval from n equals 1 to infinity of all of these in's, right? All of them, from 1 to infinity. And so, and of course this is just I1 intersected with I2, intersected with I3, and forever and ever and ever. Now, if x sub k is some element in that list from 1 to infinity, right? We know that, and remember, this is every real number, x1, x2, x3, x4. That's assumed to be every single real number, all of them, from negative infinity to positive infinity. By the way that we designed this, we know that xk is not in ik, or in any I sub j where j is bigger than k, right? Any smaller subsets, which means, it's not in, that means in particular that xk is not in this list, is not in this infinite intersection, because it doesn't appear in here. That means it's not in every interval, which means it's not in the intersection of all the intervals. But that goes for any of the real numbers, right? Because no matter how far we go down the list, we know that at x 1 billion, right, x 1 billion is not going to be in the interval I 1 billion, right? But since our list was supposedly every single real number, that means that none of the real numbers are going to appear in this infinite intersection of real numbers. In this infinite intersection of nested intervals, which means that this infinite intersection of nested intervals is empty. Because none of these real numbers can possibly be inside this infinite nested interval, right? Because they stop being in it after, if this is xk, every single real number xk will stop being in it after the kth, from the kth interval onwards. Which means none of the real numbers appear in the infinite intersection, which means the infinite intersection is empty. But that, my friends, is a contradiction. Because in the last video, we proved that the nested interval property shows that any nested intervals, any set of nested intervals, infinitely nested intervals of closed intervals, of the real numbers is never empty. We showed that it was never empty, and therefore, this is a contradiction. That cannot be true. We know that the infinite intersection of forever nested closed intervals is never empty. There will always be some element that's in there at the end of it, in the real numbers. But of course, we know that none of the real numbers on our list appear in the infinite intersection, but we assumed that was all the real numbers. But we know that this infinite so there's two contradictions here. Either the contradiction happens here, right, from showing that this infinite intersection of nested closed intervals is empty. That contradicts the nested interval property, so that's one contradiction. Or we could say that none of our numbers appear in the list, but we know it can't be empty, so by the nested interval property, there exists a number x in the real numbers such that x is in this infinite intersection, right? We know that that's true. But if it is in this infinite intersection, but we just showed that none of the real numbers, which we assumed all of them were on the list, are in this infinite intersection, then this must be some other thing, right? But that can't be the case, right? We assumed we had every single real number, and we discovered that we didn't, which is another way of looking at the contradiction. So that's two different ways of proving that it's impossible to map all of the natural numbers onto each and every one of the real numbers without missing any and hitting each one uniquely, etc., etc. That's two different ways of looking at it. Either it violates the nested interval property, or it violates the fact that we can't even make a list of them, right? We tried to make a list using the numbers between 0 and 1. Which is funny. That's kind of interesting. So we showed that the size of n is strictly less than the size of r, right? But we also showed that it's strictly less than the size of the interval from 0 to 1. So is the size of 0 to 1 less than that of r? Well, that would answer the continuum hypothesis, wouldn't it? But I just said before that the continuum hypothesis is undecidable. So if it was that easy to find an example of something between them, then that wouldn't have been such an undecidable problem, would it? So either, and we showed that this was strictly greater than this. So it actually is the case, my friends, that these have the same size. And it's not too hard to see. Take a look at this. So imagine we have a line and a circle of radius 1 divided by pi. So we know that pi is a number, right? Okay, so we don't know that pi is irrational yet. We haven't proven that, but we know that pi is a number because you can simply divide the circumference of a circle by its diameter, and you see that there's some number, 3.14, whatever, that is the ratio. We don't know if it's irrational or not, but we know that it's a number and we can utilize it. So if we have a radius of 1 over pi, then what, pray tell, is the length of half of the circle? Well, then the length of half of the circle is just 1, because the circumference of a circle is 2 pi r. So half of the circumference is c over 2, which is equal to pi r. If the radius is 1 over pi, then we just get a semicircle of 1. Half the circumference is 1. So the length of this arc here is precisely 1, just like the length of this interval is precisely 1. But if I now draw myself the real line, the real number line, this is the continuum, this is all of them. You'll notice, if I draw any line from this center of the semicircle through the semicircle to the real numbers, I associate 1 point on that semicircle to precisely 1 point on the real number line. And I can do that anywhere. Right? And as we get closer to the center of this semicircle, we sort of hover around this area. But as we get really, really close to being parallel, you know, to the top line, we really get quite far away. And as you get closer and closer and closer by picking tinier and tinier angles, you'll always be able to associate a unique point on this circle to a unique point on this line. Right? And so that is sort of a nice heuristic geometric visual proof that I can associate each number on an interval from 0 that's length 1 to the entire number line, which is to say that I can find a 1-to-1 and onto function from an interval of length 1 to an interval of infinite length in the continuum. And so they are the same. They are the same size. The interval from 0 to 1 is the same as the interval of the entire real numbers, which means any interval is the same size as the real numbers, because I could just change this ratio to be whatever I want, right? Any positive epsilon, right? This could be any epsilon greater than 0, as a radius of the circle could be as tiny as we want, right? The drawing doesn't really care how big I draw it, so it actually doesn't matter what the radius is. And so I can do this. I can associate every single point on this semicircle with a single point on the real number line without missing any, and it's a unique mapping. And so it's a bijection from any interval to the real numbers. So that is to say that any interval from A to B, no matter how tiny the difference of A and B, this is the same size as all of the real numbers. There are just as many elements in this set as there are in the entirety of the real numbers. We are able to always find a bijection from any interval to the real numbers, every time. And this is always not the same as n, not the same size as n. So that's kind of an amazing fact, right? Any interval, no matter how tiny, has the same size as all of the real numbers, yet all infinitely many natural numbers are strictly less than either of these things. Kind of amazing. And yet, you know, it is the same size as q, which is kind of fantastic too. We showed that. And of course, the real numbers, are the same size as the irrational numbers, because q is only countable, which means if we union these two together and get r, this must be uncountable if we're going to make the whole set uncountable. So that's that first part. That's all about the size of the real numbers, so that's pretty frickin' amazing that it's just this new infinity, right? It must be a bigger infinity, right? That's what we're saying here. That's really what's being said here. The infinite amount of real numbers is a larger infinity than the infinite amount of natural numbers, which is pretty frickin' amazing. I don't really know how you would interpret that as like a number or a size. It's kind of just an amazing thing to discover anyway. And I think a lot of people probably laughed in Cantor's face when he proved that to them. They probably thought there was something wrong with his proof, but I dare you to find something incorrect about that proof, because it is foolproof, so to speak. But does there exist a set A whose size is greater than that of the real numbers? Is there a set A that does that? And then, of course, there's the natural question, is there a set B that's bigger than that? And so on, right? Is there anything that allows us to make arbitrarily large infinite sets that are definitely larger than the sets below them? Yes, there is. And we are going to learn about that now, but we need to first discuss something called a power set. So a power set of a set, so P, and I usually write it like this, P of A, power set of A, is equal to all sets X such that X is a subset of A. Not necessarily a proper subset, but some subset. So to give you an example, let's let A equal the set 1, 2, and 3. Then we know that the power set is the set of all subsets of A. So what are all the subsets of A? Well, there's the set that contains nothing, the empty set. There's A itself, right? There's the set with nothing in it, there's the set with everything in it. So those are both subsets of A. Right? If everything is a subset of A, then nothing is a subset of A. And of course, there's the set that contains each of the individual elements. So there's 1, 2, and 3. And then there's the set that contains 2 of each of the elements. So there's the set 1, 2. There's the set 2, 3. And then there's the set 1, 3. And so if you notice what's going on here, each of these sets is an element of the larger power set. And so there are 1, 2, 3, 4, 5, 6, 7, 8 elements to this power set. And that's no coincidence. I will leave it as an induction proof to you to show that if A is finite, so if the size of A equals some number n in the natural numbers, then if the size of A is n, for, if it's a finite amount, it must be some integer, right? There's no half elements. So there's some integer amount of elements, then the size of the power set of A is precisely 2 to the power of n. We had 3 elements in our set. There are 8 elements in this subset, and 8 is equal to 2 to the power of 3. So this is always the case. And sometimes the power set is expressed as 2 to the power of that set. So sometimes this is what's expressed. So sometimes the power set is written as 2 to the power of A, right? Because there's some sense in which, if it's finite, and even when it's not finite, this notation is used. So the power set of the natural numbers, even though the natural numbers are infinitely large, right, is written like that sometimes, if A were the natural numbers. And so I'm going to leave this up to you as a proof. So if the size of A is some natural number, then the size of the power set of A is 2 to the power of that natural number. Maybe that's why it's called a power set. I don't actually know why, but that's what it's called, and that's a fact about finite sets. For infinite sets, we don't have that same luxury. We can't associate a number with that. But we're going to prove something pretty amazing about power sets without saying anything about the size of the set. So what we're going to do is prove Cantor's. And this blew my mind when I learned this in real analysis. This proof here is a little dense, but let's try and do it. So you just sort of have to think outside the box. It's going to be a little difficult to grasp at first. It took me a while to grasp it, but then as soon as it clicked, it was one of the most beautiful things I ever seen in my life. We're going to prove that there does not exist an onto function, f, which is a function from a set A to the power set of A. And if we cannot find an onto function from A to the power set of A, then we certainly can't find a bijection from A to the power set of A, because a bijection is a function that is one-to-one and onto. So if it's not onto, then it's not a bijection. And we're going to prove, without even once referencing the size of A, whether it's finite or equal to some number, or it's infinite, or it doesn't matter what the size is. It could be some horrendously, arbitrarily large set A. If you consider the set of all the power sets of A, it is not possible to find an onto function from this to that. And what does that mean? That means that not every element of this set is hit by an element of this. So you can find a one-to-one mapping, right? You can find a mapping where each element here is hit uniquely, right? Each element in here hits exactly one element of the power set, but you cannot find a function where every single element of the power set is hit by some element of the regular set, which is to say that there are more elements in the power set of a set than there are in the original set. And that goes for any set. Without mentioning the size, that means it will work for any set, whether it's n or r or the empty set or any set, no matter how big. And so I'm going to, without mentioning the size of A, prove to you that there does not exist any onto function from a set A to the power set of A, which is to say that you can sort of just take the power set of any set and you get a bigger set, right? So that's sort of how we get the infinitely many infinities. So let's prove this. So what we're going to do is we're going to assume there exists, for the sake of contradiction, a function f from A to the power set of A, which is onto. That is to say that every element of the power set of A is hit by some element of A. Okay? Now, remember, the power set is populated by subsets of A. So the elements of the power set are not numbers like they may be in A, they are, or whatever the elements of A are, they are subsets. So the elements of the power set are sets themselves. So because I'm saying that the element, so f is a function that takes each element of A and maps it onto an element of the power set of A. That is to say that for all little a inside of A, f of A is a subset of A. That's what that's saying. So f of A is an element of the power set of A, but it is a subset of A, right? Because the power set of A is the set of all subsets of A. Okay? So what we're going to do is define a particular set now. Now this is so clever. I just love this proof. This is so ingenious. It makes me giggle just thinking about it. Hee. Let's define B to be the set of all little a contained in big A, such that A is not contained in the subset that the function f maps it onto. So for example, if we let A equal the set 1, 2, 3, right? Then we could map 1 onto the subset 2. We could map 2 onto the empty set. And we could map 3 onto the subset 1, 2. In every case, A is not in f of A. A is not in f of A. A is not in f of A, right? Because remember, these are the elements of the power set of A. And so we're taking elements of A and we're mapping them onto elements of the power set of A. And in particular, we're defining a subset of A, which are all the elements of A who do not get put into their subsets when they, or are not an element of the subset that they are mapped to. Like in this case, right? 1 is not in the set that only contains 2. 2 is not in the set that contains nothing. And 3 is not in the set that only contains 1 and 2. So this would be a case of taking each element of A and mapping them onto a subset of A that does not contain the element that we started with. And that's essentially what this subset is. Of course, clearly, with a finite set it doesn't work, so we're not assuming anything about the set, the size of A. And we're going to show that this leads to a contradiction. So, how are we going to derive a contradiction from this? It's not too hard. So this subset definitely has to exist because there might, maybe this subset is empty, right? Maybe every element of A gets mapped to some subset of A where the element is in that subset. Maybe that always happens, in which case B is empty. It doesn't really matter if it's empty or not. It just matters that this set exists, right? It could be empty, but there could be elements of big A that do get mapped to subsets that don't contain that element. Cool? But because B is a subset of A, there exists an x in A such that f of x equals B, right? Because we assumed that our function was onto, and therefore every subset of A is hit by some element of A. Since B is a subset of A, right, it contains elements of A, then there must be some element of A that maps onto B, right? So that's not the contradiction yet. I'm just using the argument, right? We assumed it was onto, so there must be some element of A that when we apply the function gives us the subset of A, which is in particular B, that we constructed. Now, there's only two possibilities now. Either this element x is in B, or it is not in B. Those are the only two possibilities. It cannot be both, it cannot be neither. It must be one of them. And that is how we're going to get our contradiction. Because let's assume x is in B. So if x is in B, and again, x is just an element of A, if x is inside the set B, then that means then that x is not in the subset given by f of x, right? Because that's what we assumed. But that can't be the case, because what is f of x? F of x is B. So x being in B implies that x is not in B. Well, that's a bit of a problem, right? Because think about it, right? This took me a while to wrap my head around, so it might take a little while for you as well. Either this element x is in the subset B or it is not in the subset B. If it is in the subset B, so we know, we assume that there's some element x in A that gives us B when we apply this function that is onto. So either x is in B or it's not. But if x is in B, then in particular x is not contained in the subset given by f of x. But f of x is B. So x being in B implies x is not in B. That's a contradiction. Well, then in that case, it must be the case that x is not in B. Right? This is bad. So therefore, x must be not in B. X is not in B. But if x is not in B, then that means that x is not in f of x, because f of x is precisely B. By assumption of how we built B, it's all the elements of A who do not appear in the subset that they are mapped to. If x is not in B, then x is not in f of x, which implies that x is in B, which is a contradiction. So both cases, right? Both cases can't be false. They can't. One of them has to be true, or else we have a contradiction. But both of them are false. It's not possible. This is a contradiction. There is no one-to-one mapping from a set to its power set. Because we constructed a particular subset, which could be empty. It could be empty, right? It doesn't matter if it is or not, right? It may be the case that every element of A is mapped onto a subset of A that actually contains that element A, right? In which case B is empty. And if it is, it doesn't matter. We didn't have to reference the size of B. But because B is some subset of A, there must be an element of A, which we called x, which when we take f of x gives us B. Because, right, we take an element of A, we apply f, we get a subset of A. So some x inside of A has to give B when we apply f to it. And then either that element is x, either that element x is in B or it isn't. If it's in B, we get that it isn't in B. And if it isn't in B, we get that it is in B. Which is a contradiction. That's not possible. You can't have both of those things be true at the same time. And so that's the full contradiction. Cantor's theorem is true, and you cannot find an onto mapping from one set to its power set, which means as long as we take power sets of some set, we have a set that has a larger cardinality. In other words, the power set of R is bigger than R. Whatever that is. The set of all subsets of real numbers is a larger set than the set of real numbers. And of course, the power set of the power set of real numbers is strictly larger than the power set of real numbers. And you can just carry this on. You can just do this as much as you want. You can get as large as you want. These sets are getting arbitrarily infinitely large. And because we can take as many power sets as we want, we can sort of see that this proves that there is no largest set. Right? We can go as big as we want. This necessarily gets bigger and bigger and bigger and bigger and bigger, producing ever larger infinite sets, which definitely have more elements than any of the elements in the previous set, which is just an amazing fact. You can get as large of infinities as you want. Each of these represents larger and larger infinite amounts. I don't know if there's anything between any of these, and I actually don't know if this is the case. Maybe someone can answer this question. I don't know that it's true that the power set of n is equal to R, or at least the size of that is bigger, or the same. Maybe this is true, I don't actually know. Maybe someone who's more well-versed in set theory can explain this in the comments. Is the power set of the natural numbers equal in size to that of the real numbers? I don't know. But all I know is that it's an amazing fact. You can produce as many larger, infinitely large sets as you want that are all bigger infinities than the ones that come before them. And that's why Cantor's theorem is one of my favorite theorems. I think it's just a stunning, stunning proof. Just a stunning proof. Without even once referencing the size of the set, we show that this is not possible. Therefore, there does not exist an onto function from a set to its power set. And therefore, it must have more elements, right? Not everything in here is hit by an element of that, which is just an amazing thing. So I think that concludes our video for today. And that actually concludes going through chapter 1 of the text. And so in the next video, we will be doing problems. We will be doing we'll be working through problem sets. I know, I think it was a little silly for me to do it the way I did it, where I did each of the sections first, and now we're going to do problems, because I needed to use facts that would be solved in problems to do stuff in this video. So I think from now on, I'm going to do a video, problems, a video, problems, a video, problems, to get you used to it. If you'd like me to do problems, please indicate so in the in the comments. If you'd like me to just continue with the theory, that's perfectly fine. I'll just continue doing that. But if not, I will do problem sets as well. So I hope this was enlightening. I hope this was enjoyable. I hope this expanded your view of infinities and the size of infinities. It's been a pretty amazing thing that we're able to do this. So yeah, cool. Thank you for watching, and I'll see you in the next chapter. Bye-bye now.